Let's use reduction of order to write the general solution for a non-homogeneous second-order linear equation. So here is such an equation, and remember in general, the general solution to a non-homogeneous second-order linear differential equation is going to be a particular solution plus our complementary function, which is going to be the particular solution plus some linear combination of our fundamental set. So C1y1 plus C2y2. Okay, and you can take my word for it or check for yourself that this function, 1/3 x plus 4/3, is a solution to this non-homogeneous equation. So that's y sub p. So what we need now is to find a fundamental set for the associated homogeneous differential equation, which, remember, the associated homogeneous differential equation is just the same differential equation. So d squared y over dx squared minus 4 dy dx plus 3y. But the right-hand side, you just throw it away and put a 0 there instead. So here's the associated homogeneous equation, and I have sort of given us one solution to this associated homogeneous equation. It's e to the x. So now we need to find a second one, right? So we know y1, we just need to find a second solution to this, a second linearly independent solution to this equation. And we can use reduction of order. That's exactly what reduction of order is for. So we can guess that y2 ought to be equal to e to the x times some unknown function u, and then plug this into the associated homogeneous equation. So we need some derivatives. Y sub 2 prime is e to the x times u plus e to the x times u prime. Don't forget your product rule. Y sub 2 double prime is going to be, so again, product rule, e to the x times u plus e to the x times u prime. So that's the product rule for the first term. Now the product rule from the second term, another e to the x u prime plus e to the x u double prime. And then we can combine those middle two terms. We get e to the x times u plus e to the x 2e to the x u prime plus e to the x u double prime. Okay, now we can put this all into the homogeneous differential equation up here. So y sub 2 double prime is e to the x times u plus 2e to the x times u prime plus e to the x times u double prime. So that's this first term. Now for the second term, minus 4 times y2 prime right here, e to the x times u plus e to the x times u prime plus 3 times y sub 2, so that's e to the x times u. And this is all supposed to be equal to 0. Now something that I notice here is that everything here has a factor of e to the x. So if we just divide everything by every term by e to the x on both sides of the equation, all of these e to the x's are gone. So let's do that now just to simplify things. Okay, and then let's gather up all of our u double prime terms. There's only one of them right here. So that gives us u double prime. Now let's gather up all of our u prime terms. There's two of them, there and there. So we get 2 u prime and then a minus 4 u prime. And then let's gather up all of our u terms. And remember, the stuff that's in parentheses here ought to add up to 0 if we've done reduction of order correctly. So gathering up all of our u terms, there's a 1 coming from here. There's a minus 4 coming from here. And a plus 3 coming from here. So those add up to 0. So good, we did something right. So this gives us the equation u double prime minus 2u prime equals 0. And then, right, this is a first order equation in u prime, or if you like, you can set w to be u prime, and then this is w prime minus 2 W equals 0. So W prime is 2W, and this sort of equation is so common that I could just write down a solution. It's some constant times e to the 2x. Right? If you take the derivative of this, you get twice what you started with, which is what this differential equation says. But W is really U prime, so I need to integrate one more time. So U is 1/2 a e to the 2x plus a constant. But as usual, this final constant here is just going to tell us that y1 is a solution, which we already know. So let's just pick 0 for that. And since we just need an example of some function u that solves this differential equation, right? We don't need to know every function that solves this equation. We just need an example. So we can choose whatever we want for a. And just to make things simplest, I'm going to choose a equals 2 because it cancels that 1/2. And so u is e to the 2x. All right, so we know that y1 was e to the x. y2 is our first solution, e to the x, times u, which is e to the 2x. So this is going to give us e to the 3x all together. So our general solution is, remember, we have to write down our particular solution because, right, we found a fundamental set for the associated homogeneous equation, but our original equation was a non-homogeneous equation. So we have to write down particular plus complementary, and the particular solution was, what was it, 1/3? Yes. 1/3 x plus 4/3. So this part is the particular solution, and then plus the complementary solution, which is some constant c1 times y1, which is e to the x, plus some other constant times y2, which is e to the 3x. And there we go. There's a general solution to the non-homogeneous equation.